final video in Unit 2. It's called It's All About the Fundamentals. It says, you may hate gravity, but gravity doesn't care, from Clayton Christensen. So, the goals are that you be able to describe the effect of distance on gravitational and electrostatic force, that you be able to describe the effect of mass on gravitational force, and that you be able to describe the effect of charge on electrostatic force. So here's what we already know. Weight is another name for the gravitational force. So the gravitational force we've already talked about. Gravitational force pulls object towards Earth, and it can be calculated using the formula Fg equals mg. But now remember, this formula applies to Earth only. Okay, so now we said, okay, here's what we learned in the lab. There's an attraction between any two objects with mass that we call gravity. So it's not just on Earth that there's gravity, but gravity is actually what attracts the Earth to the Sun, it's what attracts the Moon to the Earth, and so on. So we learned that as you increase the mass, the gravitational force between two objects increases in a proportional rate. So if you were to double the mass, you double the gravitational force. Distance is a little bit different. If you were to double the distance, the gravitational force would cut to 1/4 of its original value. So there's an inverse square relationship whenever we talk about the relationship between distance and force. Now, there are 4 fundamental forces that everything can be classified as. We call that fundamental forces. So Fa, Ff, Fn, Fg, all the forces that we have been using can be classified as one of these 4. Okay, it doesn't matter what other forces you talk about. Some people will talk about the electrostatic force, the spring force, they'll talk about the tension force. All of them can be defined as one of these 4 forces. In fact, most of them are the first 2. The first one is called the electromagnetic force. The electromagnetic force is the interaction of charged objects. So anytime you have like protons and protons and electrons, they're both charged objects, so there's an interaction between those two. So the fundamental forces, electromagnetic, is a lot of them. The applied force, frictional force, all of those things, the normal force, tend to be these electromagnetic forces. And here's the reason why. Ultimately, you're dealing with atoms. On the outside of atoms are electrons. So whenever you have an object that comes and touches another object, you have the interaction of the electrons in the outermost rings of the atoms that actually create the force that you feel as the applied force. The gravitational force is the interaction of objects with mass. That's the Fg that we've been talking about. So almost every force that we've talked about, in fact, every force that we've talked about can be classified as one of the 2 top fundamental forces. The other 2 of the 4 fundamental forces are the strong nuclear force, which confines quarks into hadrons, which basically means it's what it holds protons and neutrons together in the nucleus. And then finally you have the weak nuclear, which is basically the cause of radioactive decay. All right, Newton had a version of how he explained gravity. He built on the work of others, and he developed this formula right here, where he had, this wasn't actually here, okay, he said that F is proportional to m1 m2 over d squared. Okay, so in other words, if you increase the mass, you increase the force. If you increase the mass, you increase the force. If you increase the distance, you decrease the force by quite a bit. This was Newton's version, and the reason why he's considered a genius by many is because he developed the first universal law. It's the one that applies everywhere. It's the same reason why an apple falls to the ground from a tree, as the reason why the moon falls to the earth, which is the reason why the earth falls to the sun. It's the first example that we have of a universal law. Okay, and that's what we talk about here. It's the first one that can be universally applied. So now we come to the fundamental question. It says, sketch a gravitational force versus mass graph and state what happens if the mass of the Earth were to suddenly double. So the first thing is we're going to put force here. We're going to put mass here because force depends on mass. Mass does not depend on force. And then what we're going to say is as we increase the mass, we increase the force in the same amount. So we're going to get a relationship that looks like this. This is a proportional, sometimes people refer to it as a linear relationship, but as you double the mass, you double the force. Now, it says what happens to the weight if the the mass of the Earth suddenly doubled. So if you're here and you're on Earth and you have a weight of, let's say, 1,000 newtons, and all of a sudden the mass of the Earth doubled, you would all of a sudden feel a much stronger attraction, and your force would be 2,000 newtons. So you would double your weight if the mass of the Earth doubled. What can you do to decrease the gravitational force the Earth exerts on you? Well, there's a couple of things that you can do. So if you were to look at the Newton's proportionality, which was this, the first thing that you can do is you cannot change the mass of the Earth. I guess technically you could get a bucket and you can start throwing water into space, but that's not realistic. So then you're left with the option of, okay, I can lose mass. So if you lose mass, that's the first thing that you could do. If you decrease the mass, you decrease the force. And that makes a lot of sense, but sometimes you want to do it another way. How could you decrease it without changing your mass? Well, the other option is you can increase the distance. If you increase the distance, you also decrease the force. So somebody said, well, how am I supposed to increase the distance when I'm on Earth? And the simple answer to that is Earth is not flat. It has, structure and has altitude. If you were to go to the top of a mountain, you would weigh slightly less than you would at the base of the mountain. Now, it's not a huge amount, but it is a way that you can decrease the gravitational force. If you were to somehow take an airplane up, okay, if you're in a plane or a hot air balloon, okay, if you're up here, it would be even less. So if you increase your altitude away from Earth, you actually decrease the gravitational force of Earth on you. Okay, the next one says, a comet experiences a force of F when initially at a distance of d. As the comet approaches the sun, it evaporates, losing 1/3 of its mass and reaching 1/4 of the original distance. So in this particular case, it is 1/3 of its original mass. Okay, so if I have this is originally what I have, m1, m2 over d squared. Now, the mass of the sun doesn't change, so this is going to be a constant number. But in the new situation, I'm going to have 1/3 of m1, and I'm still got m2. And in this case, I'm going to have 1/4 the distance. So 1/4 the distance. But remember, distance is a squared term. So in this case, I can get this exact same expression. Okay? What I've done is I've decreased the gravitational force by 1/3 because of the mass. So that's that 1/3 right here. Okay? But then what I've also done is I've done this. 1/4 is 1/16, but it's on the bottom. So now if you're not sure how to do this, you can actually enter this in your calculator. You can say 1 divided by 3 divided by 1 divided by 16. Now it's really important that you use the parentheses, but if you didn't know this, if you have 1 over something in the denominator, that actually flips up to the top. So another way of being able to write this expression would be 16 over 3. And the next one, it says, astrology suggests that the position of the planets relative to the Earth can affect your personality. How different is the gravitational force that Mars exerts on Earth at its closest and farthest approach? So if we were to look at this, we're referring to the distance. And if you look, we're going to call this first distance d. So we have d, and then we have what amounts to 8d. Okay, so we have the distance and 8 times the distance. Remember, distance is a squared term. So if you were to square this term, okay, you would realize that there is a 64 times greater gravitational pull when it's just at d. So there's 64 times more gravity when it's at its closest approach than when it's at its farthest. But what you should realize is that even though it's 64 times more, it is still much, much, much smaller than the gravitational force of the sun. In fact, it's 22 million times smaller than the gravitational force of the sun. So could it affect your personality? No. It's too small to make any sort of significant difference. Okay, Cavendish actually came around and he took Newton's proportionality and turned it into an equality. And what he did is he had this brilliant setup where he had 2 metal balls, and he was actually able to figure out the gravitational attraction between them. When he did that, he actually came up with this. And this is what Newton's law of universal gravitation is actually called. This is the equation. Now, as far as this is concerned, this is only a mastery level question. I will not ask you to use this equation other than on a mastery level question. The only difference between Newton's proportionality and this equation is the g term. The g term is what Cavendish contributed, and it is always a constant value of 6.67 times 10 to the minus 11th. So we can go ahead and calculate out what the gravitational attraction is between two ice skaters separated by 0.5 meters. And so what you do is you would say, okay, I know g. G is a constant. It's always 6.67 times 10 to the minus 11th. Okay, I know that the mass of the first object is 60 kilograms. I know the mass of the second object or person is 45 kilograms. I know that the distance between them is 0.5 meters. And I can use the equation F equals g m1 m2 divided by d squared. At this point, you would plug in. You would say 6.67 times 10 to the minus 11th, which is a very, very small number, which is why gravity is very weak, times 60 times 45 divided by 0.5 squared. Okay, whenever you do this and you actually plug in your numbers, you end up getting a very, very, very small value of 7.2 times 10 to the minus 7th newtons, which is a very, very, very small number. It's 0.0000072 newtons, which is extremely small because the gravitational force is very, very, very weak. In order for gravity to have any significant pull whatsoever, you have to have an object like a moon or a planet or a star, something that's so massive that it can pull things in. Now, in the second part of the lab, we started to look at something called the electrostatic force, and we said increasing the charge increases the force. Increasing the distance decreases the force. Very, very similar to what we had with Newton's law of universal gravitation. And we also had something different. We talked about the orientation of the charge and how if you had two positive charges, they would repel. And if you had a positive and a negative, they would attract. So we come to what we call the fundamental law of static electricity. And we'll talk about this again when we talk about electricity. But opposites attract and likes repel. So if you have two positive charges, they will repel or move away from one another. If you have a positive and a negative, they will attract. So we come to George Augustin de Coulomb. He was the one who described the relationship between charge, force, and distance. And he said that if you double the charge, you double the force. And if you double the distance, you quarter the force. So it's a whole idea of that inverse square relationship. And as a result, we can answer some questions. So what is the fundamental law of static electricity? And that is opposites attract. Now you may be asking yourself, well, what is this all about? This picture right here, this is a music video by Paula Abdul in which she's singing the song Opposites Attract. So, which graph represents the relationship between electrostatic force and distance? Remember, as distance goes up, force goes down. So we can immediately eliminate these two right there because those are saying as distance goes up, force goes up. So now the next thing that we have, it says, is it directly proportional or inversely proportional? Or square, is it a squared relationship or directly? And it's a square relationship. So as you double the distance, you quarter the force. This one says, what will the path of the particle be? So this is going to use the whole idea of opposites attract. If you were to look as you fire this electron through these charged plates, it's actually going to move towards the, drew that to the wrong side. It's actually going to move towards the positive plate because opposites attract. And so it's going to take a path that kind of curves it upwards towards the top plate. The next one, it says two charges, Q1 and Q2, are separated by a distance to provide a force of F. So I've got Q1 and Q2 that are separated by a distance. Remember, distance is squared. That results in a force. It says the distance between the charges is doubled. So instead of d, I have 2d, which is still then squared. It says at the same time, the magnitude of the charges is increased from 3 and 5. It wants to know what the new value of the term f is. So if you look at it, this is pretty easy. You have this 3 and this 5, and those are multiplied, and they're on the top. So 3 times 5 is 15. And on the bottom, you have this 2 squared term, which is 4. and then you have Q1, Q2 over d squared. Well, remember Q1, Q2 over d squared is just F. So the new force is going to be 15 over 4 of whatever F is. So it's about 4 times as much. Now this right here is called Coulombs Law, and once again this is a mastery level question. You'll only be asked to calculate this using a mastery level question. This is, once again, you see the very similar nature in it. You see Q1, Q2, d squared, and you see this, which is a constant. Now, instead of it being a really small number, Coulomb's constant, which is the Kc, it refers to a very, very large number. It's 8.99 times 10 to the positive ninth. So it ends up being a number like 899, and then there's a whole bunch of zeros. Okay, so whenever you do that, I think there's one more. Okay, it looks something like that. So the electrostatic force or the electromagnetic force is a very, 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 very strong force. So it says determine the force from two 1 times 10 to the minus 4th Coulomb charges separated by a distance of 1200 meters. So remember when we talked about the gravitational force, we had 50 and I think 60 and 45, and they were separated by 0.5. Here we're going to talk about two exceptionally small charges, 0.0001. And we're going to put them very, very far apart. So we want to know what the force is. We know Coulomb's law, or Coulomb's constant, is 8.99 times 10 to the ninth. We know that the Q1 is 1 times 10 to the minus 4th. We know that Q2 is 1 times 10 to the minus 4th. And we know the distance between them is 1200 meters. So we can say F equals K Q1 Q2 over d squared, or 8.99 times 10 to the ninth times 1 times 10 to the minus 4th times 1 times 10 to the minus 4th divided by 1200, and then we can't forget to square it because it's a squared term on the bottom. Whenever you take those and divide it out, you end up getting something like 6.2 times 10 to the minus 5th newtons. Now you may be saying to yourself, well, that's a really small number, and you're right, it is, but that's because it's a really small charge separated by a really big distance. It's almost 3/4 of a mile. So you end up getting more of a force than you do for the gravitational force between two people who are right next to each other. So the electromagnetic force is much, much, much stronger than the gravitational force. The last thing that we should look at is applications of Coulomb's law. You can actually use Coulomb's law to, it's the normal force, and we talked about that earlier, and you can use it to electroplate metals, but really what we want to talk about is comparing Newton and Coulombs. If you look at these, a lot of times these go hand in hand because they're both inverse square laws with reference to distance. Okay, if you look at the format of them, they're almost the exact same. The electric force is equal to a constant times charge 1 times charge 2 over d squared. The gravitational force is force equals a constant, mass 1, mass 2 over d squared. They're often compared because they're basically the same formula. Remember, both of them are fundamental forces. And when you look at two fundamental forces that have almost the same version or the same formula, it really brings up a lot of questions about, hey, what about these other fundamental forces? Do they have the same formulas?